Okay, so I'm talking about household-based inference of infection transmissibility. I'll start with acknowledgements and background. So this is a combined University of Adelaide and University of Melbourne project funded by Defence, which may sound a little odd initially, the DST in Australia, and something called ITC PAC. The PAC stands for Pacific. I forget what the ITC stands for in the US military. They were concerned with epidemics spreading through the military, and this work began in 2017, actually, when I was still finishing my PhD, but sort of a postdoc began then. They were initially concerned about influenza, and then we sort of looked at SARS as well, and then something else came along. I forget what that was, but some other epidemic came along. So there's a combination between some inference work done in Adelaide and a decision support system done at the University of Melbourne. At least in how it was initially proposed, our inference work would feed to the decision support system at Melbourne. I'm not going to talk about the Melbourne side of it today, and actually we sort of decoupled a bit anyway. My work is supervised by Andrew Black and Josh Ross at Adelaide University, and it builds on stuff that they've both looked at in the past. So they've done some stuff looking at household-based models for epidemics in different contexts. And in particular, the plan when an epidemic came out, and this is the health management plan before COVID came along, which is probably going to be totally revised now. But the idea was to monitor the first few hundred, and then it wasn't always up to 100, so it became renamed to first few X households with an infection, and these households will be carefully monitored. They would get daily phone calls about how many have been infected in the household, any new infections, and perhaps even do some serology to test them, get definitive answers, catch asymptomatic cases. The daily infections, and these would be loaded into a database, and from that we could get good information on what's going on with the latest epidemic. A household model is chosen because obviously the infection rate is different, or you would expect the infection rate to be different within a household compared to individuals in different households. Now, traditionally, the parameter you look for in an epidemic is R0, the number of people infected by a single person in an otherwise uninfected population. But in a household-based model, someone has decided to call this R star, and it's just the same thing for households, number of households that a household will infect. And that becomes a critical number. You can actually have R0 greater than 1, but it will not take off if R star is less than 1. And the intuition to that is that a new person might go and infect their whole family, but as long as it doesn't spread beyond their family, no one's really concerned. So you might come along and infect 4 other people. That might say R0 is greater than 4, but it doesn't matter because it's not spreading through the rest of the population. So our model became a, well, 3-step, but actually 2 large main step process within household and between household. There's a model there. I'm not going to talk it through in a 5-minute talk, just to show there's a compartmental model. And if you look closely at it, the rectangle there, you'll see that people are infectious before they show symptoms. That is because that's a COVID-based model. We've written numerous models. Now, from this FFX data, we infer various within household parameters: the mean time in each of the compartments, the probability of an infectious person being symptomatic, and the within household infection rate. So these are all done in a Bayesian framework. That bit in brackets, that took up several months of my life, but I'll summarize it in 8 words: particle marginal metropolis Hastings algorithm with importance sampling. I'm not going to talk about that in a 5-minute talk again, but that, if you're interested in those topics, I've done quite a bit of work there. And we get the joint posterior distribution of these within household parameters. The step 2 is the between household inference. And now we, compared to looking at individuals, we actually look at households. We look at how many new households are infected each day. And if you can, so you've got that number that we call Y. Now, if you can also estimate this number capital lambda, I think that's a capital lambda, of the effective number of infectors per day, then you can get an estimate of alpha simply using the conjugate prior technique. So other papers have come out estimating this lambda using observed data. We're trying to get it using getting it directly from the between household parameters. This is actually quite a tricky process, calculating this lambda k. And when I say complicated by various issues, that bit in brackets is again, took up a couple of months of my life, but I'm not going to talk about it too much here, especially dealing with growing and shrinking population size, and you get some unexpected effects that your predictions aren't quite what you expect because it perturbs your distributions. As the final step, you can then combine alpha with within household parameters, and you can get either I naught or R star. Thank you, Matthew, in his earlier talk for talking about forecasting. So I quickly went in and added this sentence. Wasn't going to talk about it too much, but yes, we also use these for forecasting. There's just a little example here. So the blue shows the number of infections in the last 7 days. The grey shows the true R star, and you can see that it takes a few households to actually converge to a sensible value. And then when it changes, we track it. We don't track it exactly because we're looking at the last 7 days, and you've got to get some sort of trade-off between using lots of data and lots of days or being very immediate. And so we're looking at the last 7 days, and the dotted lines are effectively the range of confidence. COVID lessons. So then COVID came along, and we had to think about redoing some of the stuff. Firstly, we were assuming a fairly static situation where maybe countermeasures would apply once, and we would look at the whole history of an outbreak. What has happened, and especially in March and April, and perhaps also in Victoria more recently, is countermeasures kept changing almost at a daily interval, it seems sometimes. So you can't go looking at infection data from a month ago because things have changed. So we had to, and that was just an assumption in our method that we had to change. We also didn't really think too much about what happened when the outbreak size was decaying. We had to think about that, and an earlier method we used was assuming it was always growing, but where actually people get quite interested in the R naught or the R effective or the R star when the infection is actually falling. For our particular work, it actually turned out quite difficult to apply to COVID because getting household data was a lot more difficult than we anticipated. Health departments were very busy, and Australia has all sorts of privacy requirements. So people keep a diary, but then they've got to anonymise the data and all that, and you would think that would be easy, but it takes a long time. But our collaborators in the military, who were looking at a military context initially, spreading through barracks of soldiers, that they were less concerned with that in any case. And also a nice problem to have is that there was not a lot of Australian data to work with because we squashed the epidemic in most states quite quickly. So the current focus, I have not been, apart from a little bit of work early on, I haven't actually been working on the COVID directly, but we work on refining this method because as we go through it, we keep seeing new challenges and papers in preparation. So I can't see the clock, but hopefully I'm more or less on time. Thank you.